So in the world today, we have a problem, and it's a really big problem. It's a problem that my research project is focused on, my entire lab is focused on, and more importantly, a lot of people's entire life work is focused on. It's a problem that Dr. Rothman actually gave me a really great introduction for in his opening statement. And this problem is that fossil fuels are really, really awful for our environment, but we are still incredibly reliant on them. And we really have to find an alternative if we want to keep living on this earth. I'm Rachel Garwick. I'm working in the Menard Lab in the Department of Chemistry and Biochemistry under the mentorship of Samuel Jacob. My project is on the synthesis of bimetallic krypton catalysts for ammonia oxidation. My research is proposing that hydrogen can be a clean alternative to fossil fuels, but it's not perfect. And as you can see, I'm proposing that hydrogen's better, but I'm working on ammonia. So the big question is, why ammonia? Well, hydrogen is not a perfect solution. It's really difficult to store. So we're proposing that we use ammonia as a storage medium because hydrogen can be gathered from the oxidation of ammonia, and it's a lot easier to work with. But that's not the only reason. The process of making ammonia is already highly refined with the Haber-Bosch process, and it's used not only in many places in this country, but in the world. So there's a lot of countries that have ammonia. And there's a big question, because I said my entire lab is focused on this. And so one thing that somebody's working on is water, because, I mean, we live at the beach, there's so much water. Why not use water? Well, we think that ammonia would be an interesting alternative to water, because it's a lighter compound, and it has more hydrogen by weight than water does. So if this were being you put in something, say a fuel cell in a car, where there is a limited carrying capacity, you could potentially get more fuel out of less weight. And so this summer I had 3 main goals. And the first goal was to synthesize something called a cryptand. And a cryptand is a big, complicated molecule, and the significance of it is that we have to make it before we can make the actual complex that we want to make. And so this was a 5-step synthesis, and I really wanted to be able to successfully go through each step by the end of the summer. And I wanted to do this because in order to make our complex, we have to add metals to the cryptand. And I wanted to add those metals by the end of the summer. And we also wanted to refine our synthesis a little because it's not super efficient in every step. So we wanted to try and see if we can improve that a little. And this is the process of making our cryptand. We start with just plain starting material, and then we add an iodine, add a benzene ring. In the 3rd and 4th steps, we make substitutions for some functional groups. And then eventually, after 5 very long steps, we end up with our full krypton ligand. And I put the yields underneath each of the steps, and as you can see, some of them have really bad yields. So we wanted to try a few different things to improve it. The first thing we wanted to try was to make a substitution for a functional group before we added a benzene ring. Because if you'll notice, in the original synthesis, all of the additions were made before any substitutions. So we wanted to switch it up and see how that would work. And unfortunately, we found out it didn't. We were able to successfully synthesize this compound, but we couldn't get it to react any further in the synthesis. But we're scientists, we're researchers, we don't give up after one thing fails. So we tried another method. We tried to skip the 4th step completely and go from step 3 to our full cryptand ligand. And this was successful. We could synthesize the cryptand in 4 steps instead of 5. But you know, this makes it sound kind of simple. You put everything together and eventually you get out this nice one product. But that's not how it works. Nothing is ever simple. So one thing we have to do is isolate the products, because after a reaction is made, we have byproducts, we have unused starting material, we have so many things along with that one compound that we want. So one of the things we do is called column chromatography. And this isolates compounds by polarity. And so every compound has a different polarity, even if it's only slightly different. So this is really effective because you can see that it'll isolate the different compounds into bands right here. And you can collect the different bands into different flasks, and you can just take the band that you want, and that will hopefully be your compound. But it doesn't always work for everything, so another method we use is called recrystallization. And this In recrystallization, you take the products that you make and you dry it down into a powder or an oil or whatever it makes, and then you redissolve it in another solvent. We use methanol because ideally you would use a solvent that only your compound isn't soluble in, and so your compound will crystallize out and all the impurities will stay in the water. And so it's great, we have our compounds now, but we need to make sure that it's actually what we want. So we use something called nuclear magnetic resonance spectroscopy, or an NMR. And this is just a picture of an NMR machine we have at UCSD. And what an NMR gives you at the end is this graph. And in the graph, you can see different peaks. And what an NMR does is it identifies different groups of hydrogens, and it represents them as peaks on a graph. And depending on where the peaks are, you can tell which group of hydrogens it's trying to represent. And NMRs are great for telling us what we have, but they're even better for telling everyone else what we have, because chemists are not very trusting people, so they need proof for everything you do. So where's my proof? Well, it's right here. What I've done is I've taken the products from each step of the synthesis and I've just added in the hydrogens that you don't normally see in a line drawing. And I've color-coded them so that you can see which peak they represent on the graph, or the graph represents for them. And so in this first step, we have 3 different groups of hydrogens and 3 different peaks. And you can see the top hydrogen goes with the peak on the very right. Those bottom 2 hydrogens go with the middle peak. And these red hydrogens on the outside go with the very right peak. And in the second step, we just added a benzene ring. And so you can actually see the same 3 peaks, and they'll be in the same 3 colors. And they're in about the same spots, but now there's just 3 more peaks. And again, it's just green to green, yellow to yellow, purple to purple. In the third step, we made a substitution for the outside hydrogens. And you can still see the same peaks in about the same places. The only difference is you don't see a red peak anymore. And this actually happens because of the way those outside hydrogens are interacting with our solvent. But we don't expect to see the peaks, so that's actually okay. And again, in the fourth step, we made another substitution, and all the other peaks are in about the same place, and the red peak appears again, a little different than it was when you last saw it. So for this fifth step, it's our full cryptand. And like I said before, it's a big, complicated, 3-dimensional molecule. And I really could take the time to break it down and explain which peaks go to which hydrogen on the graph, but given time constraints of this presentation, I'm going to have to ask you guys to just trust me on this one. So moving forward, we hope to make the full metal complex. And I said it was a bimetallic complex, and that basically just means we want to add 2 metals to this. And you can see the spots where we're hoping to add the metals here and here. And if you'll notice that the metals we're hoping to add are all 3rd row transition metals, because they tend to be in greater abundance than 4th or 5th row. So there's already so many of them, why not make use of it? But that's more of a short-term goal. This is something that we can achieve feasibly pretty soon. What we are really hoping to get out of this project in the long term is something called a catalytic cycle. And this is the cycle that we're proposing. Each of these semicircles represents this compound. And so what we're hoping is that we can attach ammonia, or 1 ammonia to each of the metals, and then just keep oxidizing it and oxidizing it until there's no more hydrogens or protons left. And at the end, you'll end up with just a compound that has 2 nitrogens on it. And then you can get rid of the nitrogens, add in 2 more ammonia, and just keep repeating in the cycle. So we can reuse our starting material. Or not our starting material, but our end product. I'd like to acknowledge my entire lab group for being amazing and helping me with so much throughout the process. But I'd like to give a special thanks to my PI, Gabriel Menard, for giving me the amazing opportunity to work in his lab for this summer, and my mentor, Samuel Jacob, for his endless amount of patience through this entire process. Thank you. If there's any questions.